I wanted to know what you think about, you probably heard of Bill Gates endorsing a technology that could turn spent uranium fuel into clean energy. And I was wondering what your what your perspective is on this.
I do not know much about Bill Gates' suggestions, but certainly the question of safety is a central issue to nuclear. It was discussed by all the present speakers here. We know that the nuclear energy implies production of a large amount of waste, which is long-lived waste. They live over hundreds of thousands of millions of years. And this waste is also having a lot of physical and thermal and stability problems. I think the best example is coming from the fact that the American program based on Yucca Mountain, which is 60,000 tons of fuel, spent fuel, to be put underground in a desertic area near Las Vegas, has been actually being cancelled by the present administration of the United States because of the fact that it's not an acceptable solution. And without a clarification on the question of the waste, I think many of the other questions remain open. So I do not know how you can avoid the presence of a substantial amount of waste for a very long time under present circumstances, unless you do something like what's called burning of the waste by helping it with ADS, accelerator-driven systems, which are interesting possibilities. They're being developed in many places in the world, including India, by the way. And they could be an alternative solution. Until such a solution comes, the problem of the waste remains an open issue. In particular, many of the small countries have been developed here, discussed here by previous speakers, about the possibility they have to put their waste somehow into safety. Now, let me tell you, there is a rule which is applied everywhere worldwide, which says that no country can send the nuclear waste to another country. So each country has to maintain and to protect and to preserve the presence of nuclear waste, which is produced by its own industry. So many of the developing countries are coming up here, and they have relatively small amount of nuclear energy to produce. We gave the example of Slovenia, we gave the example of other places in Europe as well. I mean, do you want each and every one of those countries to be able to build its own nuclear repository? The answer is probably no. There is no way in which you can do that. So the question of building up a nuclear repository, which is not simply based on each country having the output, is certainly a very important question. I'm sure that the Commission, the Vienna Energy Commission, will certainly have something to say to this point. Can every developing country have its own deposit for waste, even if the amount of energy emitted is small? This is a real question which is open.
Thank you, Mr. Olgert. There is someone has another question. Yeah.
Yeah, I represent another NGO, actually two of them, International Sustainable Energy Organization in Geneva, and ISO, which is a counterpart of ICIC you have seen before. Now, we defined in ISO, in the Committee of Energy Systems, what is sustainable and renewable. And all the mineral energy sources are certainly not renewable nor sustainable. So you should maybe correct this. And in January, we have actually a world conference to open the Sustainable Energy Year, which is next year, as announced by Ban Ki-moon, the Secretary General of the United Nations, in a wonderful video. There is a conference on sustainable energy covering all the solutions, including nuclear, all of them, to make a master plan, a roadmap for this century, for the whole century. And we'll have forecasts every 10 years which technical solutions, covering all the renewables, of course, can contribute to this tremendous growth of energy consumption, especially electricity consumption, with all the electric mobility and so on. So I invite you to see a program on the table. There's an invitation, and I hope some of you can join in January, 10th to 12th of January, at the ILO. because energy has a lot of connection with labor. In Germany, for instance, there's several 100,000 jobs in wind power. So we have this at the International Labour Organization to discuss energy forecasts and the labor implication. Thank you.
Okay, thank you. Does someone have a specific question for one of the speakers?
To your right.
Yes, hello. My name is Amit Pathare. I'm an Indian but based in Brussels with JDF Suez. I have one question each for Mr. Cameron and for Dr. Rubbia. For Mr. Cameron, you showed us the levelized costs of nuclear. Could you please clarify what is the underlying assumption on the capital cost of the new generation of nuclear, which you estimate, which lies behind these numbers? And secondly, for Dr. Rubbia, could you please also elaborate on the usage of water for thorium-based nuclear reactors as compared to those of the current generation of the U-235 reactors? Thank you.
Yes. Pelaron, you can start.
Okay. Very quick answer, I think. We have produced a very big document called the Projected Costs of Electricity in 2010, which gives all the assumptions, but basically the numbers are as supplied to us by the member countries. So, of course, they vary between the numbers supplied from China as opposed to the numbers supplied from Switzerland at the time and France. So I can't really give you a number, but if you look at the book, you'll have all those numbers. There's several pages of all the numbers that people quoted for the different reactor types and in the different countries. And in the end, there are two numbers that are important. One is the overnight cost, and secondly is the financing cost. And it's the financing cost that we've analyzed in some detail.
Okay. May I try to briefly... Oh, this is not... Okay. No, it's not. There we go. Let me try to answer this question very briefly. The question of producing thorium is produced in a variety of ways. There are two basic solutions. Let me concentrate on one of them, which is the one of molten salt. It is a salt, it's a fluoride, which contains as a liquid most of the components which are responsible for the production of energy and the energy production of a reactor. It contains fluorides of most of the elements which are produced, and it is not pressurized. It's a swimming pool. It's at normal pressure. Therefore, there is no difficulty or risk that the system will eventually come out if the pressure or the temperature become excessive. The second important point about the thorium situation is that the safety is not probabilistic. It's not a question of adding one probability after the others, make the probability small but finite, but rather is deterministic. One can show that this kind of reactors, for physical reasons, will not be able to produce the equivalent of meltdown, which is the reason why Fukushima had, in fact, these major problems. Both thorium and uranium uranium-238 are breeder reactors, which have the characteristic, as I mentioned at the beginning, to reach a much higher extent of utilization of nuclear energy, over an order of magnitude, maybe 2 orders of magnitude more efficient in producing for a given product at a certain amount, 200 times more energy for the given product. So it's a fantastic factor which allows one to develop situations in which the separation between renewable and non-renewable energy becomes academic. If you have 20,000 years, what difference does it make if it's renewable or not renewable? All these systems the two systems are fundamentally different, however. The system with plutonium, which is the result of uranium-238, can only work for a fast breeder. Fast breeder is a reactor which normally has been very vastly developed, but it requires essentially liquid sodium, for instance, as a coolant. The best example that is superphenix, which is well known to many people around the system. There are other examples of that. There is Monju, for instance, in Japan and other places. Many countries have abandoned the fast reactor problem because of questions associated with safety of liquid sodium. The reactor coming from thorium, on the other hand, can operate on thermal. It can operate also neutrons which are not very different than the one used in an ordinary reactor, because they are operating with an energy spectrum which is around a fraction of electron volts. So it uses commercial standard system. So in summary, both thorium and uranium can be used as breeders, but the uranium breeder can only work with fast neutrons, while the thorium breeder can operate and will operate essentially with thermal neutron. This is a major advantage when it comes to that. The other important question, that most of the breeders do not produce very long-lived waste, because the waste is remaining in the waste is no longer waste, is seed, because the material is used and reused again until it's fully eliminated, which solves another very serious problem, which are no long-lived radioactive component. In fact, most of these machines propose to a system in which the bulk of the radioactivity only lasts few hundred years rather than many tens of thousands of years. Thank you.
Thank you, Professor Rubbia. I think, yes, it's necessary to conclude the session. I will firstly thank for all the speakers for their presentation. And yes, the coffee break is not cancelled, it's only delayed. The coffee break is now until 4:45. Thank you very much.